Hello everyone, I am Amitesh Roy, working with Professor Sujit at IIT Madras. Today I'll be presenting on the flame dynamics during intermittency and secondary bifurcation to longitudinal thermoacoustic instability in a swirl stabilized annular combustor. Before I begin, I would like to thank the Office of Naval Research Global for their help and in particular Dr. Ramesh Kolar. Gas turbines and aircraft engines are primarily concerned with the emission of carbon dioxide and NOx. Now, among these two emissions, there is always a trade off. So, do we want a better fuel efficiency, which will lead to a lower carbon dioxide values and higher NOx levels, or do we want lower NOx levels but at the price of fuel efficiency? Now we know that NOx is a much more poisonous and much more potent greenhouse gas. Therefore, we always wish to reduce the amount of NOx emissions in the upper atmosphere as well as the ground levels. Now, if we look at the trends of the past few decades, there has been a steady increase in the amount of NOx emission due to aircrafts. Now, this is only going to increase in future when the demand will climb even higher, demand for air travel. Therefore, in order to reduce the amount of NOx that is being emitted, there needs to be a significant technological progress in gas turbine combustion technologies. Now, NOx levels are generally increased if the combustion temperatures are high. And similarly, if one is operating at equivalence ratio close to 1, you would observe NOx levels to be again very high. Therefore, we have an operability limit. The key here is to then operate at low temperatures and low equivalence ratios. Now, this leads to the this is being achieved currently in the gas turbine industry through lean premix pre-vaporized combustion. However, this technology is particularly challenged due to the observation of combustion dynamics. Now, combustion dynamics contains thermoacoustic instability, where we observe large amplitude pressure oscillation due to a feedback between pressure and heat release rate in the system, which leads to wear and tear of very expensive combustor parts and can also lead to combustor failures. And on the other hand, we also have lean blowout, where there is a complete quenching in the engine. In the present study, we focus on thermoacoustic instability inside an annular combustor. During stable operation, we observe that the system is, the heat release rate oscillations are are not very high, and the pressure oscillations are also very low. So this state is known as combustion noise. On the other hand, we have the state of unstable operation, during which we have the heat release rate being we can see that the heat release rate is quite violent in this case, and there is a periodic oscillations of very high heat release rate. This state is known as thermoacoustic instability and is always associated with a very high pressure oscillations. Combustion or thermoacoustic instability develops through a complex feedback loop between the turbulent flow fluctuations, unsteady heat release rate fluctuations, and acoustic pressure fluctuations. Thus, there is a complex interaction between flow, flame, and acoustics that we need to understand in order to mitigate the thermoacoustic instability in aircraft and gas turbine engines. We study the same in annular combustor. So we perform experiments in a lab scale turbulent annular combustor, which is based on the designs of EM2C combustor and the Cambridge combustor. We have a air fuel inlet, which leads to a settling chamber from where it is guided into this burning tube, which is equipped with a swirler at the end. Combustion takes place between the inner and outer duct, therefore inside this annular chamber. There are in total of 16 burners that we have in the system, and each of these burners are equipped with a swirler. The swirler is the primary flame stabilization mechanism used in the present experiments. In order to make acoustic measurements, we mount 3 pressure transducers on a waveguide onto the combustor backplane at these 3 locations. In order to image the flames, we have an air-cooled mirror from which we measure the flame at the uh, right after right after the swirlers. Now we image since we have steel inner and outer ducts, we only image 8 burners. So the swirler has a 60-degree angle, which leads to a swirl number of 1.15. We use LPG gas as the fuel, which is partially premixed. We ignite through the use of a pilot diffusion flame. Pressure measurements are taken at a sampling frequency of 10,000 hertz, whereas for optimal optical diagnostics, we have a chemiluminescence measurements, which is taken at 2000 hertz using a phantom camera. This is the entire combustor operability map. In the present study, we only focus on this particular operation range, where the equivalence ratio varies from 0.3 to 0.6. The bulk flow velocity remains more or less constant at around 8.5 meter per second, since we only vary the fuel. The Reynolds number is again constant at around 8600, and thermal power varies between 40 to 80 kilowatts. For more information, you can refer to Singh et al. ASME JEGTP. This is recently accepted for the other states. So when we increase the equivalence ratio at the said condition, we observe there is a transition from combustion noise to thermoacoustic instability, but this takes place through two intermediate state. For state 2 is the state of intermittency, whereas state 3 is the state where we observe low amplitude limit cycle oscillations. Thus, we observe of secondary bifurcation in a turbulent annular combustor. So this is the first experimental observation. The present transition does not take place through any frequency change. The frequency we observe remains almost constant throughout the transition, and it is around 220 hertz, which corresponds to the first longitudinal mode of the combustor and the plenum. During combustion noise, we observe low amplitude periodic oscillations and broadband spectra. During intermittency, we observe switching between periodic oscillations, periodic oscillations being of the higher amplitudes. During low amplitude instability, we observe amplitudes of the level of 400 pascals, 300 to 400 pascals. So this is the state of limit cycle oscillations with a sharp frequency in the spectra. And finally, we observe the state of high amplitude instability, which has an order of magnitude higher amplitude than low amplitude instability. So in order to understand why we observe secondary bifurcation, we need to consider we can consider a general van der Pol oscillator, where we have a very simple general source term. Now, if we have this kind of a source term, we can consider that mu2 is equals to 1. When we consider that, we observe that there is a stable supercritical bifurcation to a stable limit cycle. However, if we change mu2 to -1, we observe that the same stable limit cycle branch becomes unstable. And in order to stabilize that, we need to include higher order nonlinearities. When we do that, we obtain a subcritical bifurcation. In order to get a secondary bifurcation, we need to incorporate sixth order nonlinearities into the system. Therefore, we have two classes of systems, where first we have low amplitude limit cycle oscillation through supercritical bifurcation. The second, we have high amplitude limit cycle oscillation through subcritical type bifurcations, where we have normal subcritical Hopf bifurcation and a secondary bifurcation. Thus, secondary bifurcation results from the inclusion of higher order nonlinearities in the system dynamics. We ignore the odd order terms because they become identically zero when when averaged over time. Now we focus on the flame dynamics observed during different states of combustor operation. First, we consider the state of intermittency, which has periodic and periodic fluctuations. During a periodic pressure fluctuations, we observe that the heat release rate is very incoherent, and the flame dynamics is again incoherent. Whereas during periodic part of limit cycle oscillation, we observe that from these phase averaged images at the pressure maxima and minima, that there is some flame structure that we observe. This flame structure is associated with the swirling some coherent swirling motion imparted due to the because of the swirler, as well as these periodic pressure oscillations. Now we are interested in investigating the local flame dynamics. In order to do that, we consider a box of this size, which is like 1/4 of the burner size. So we sum up all the intensities given in this kind of a box for all the burners. For each of the burners, we do a band pass filter around 220 hertz, which corresponds to the frequency of limit cycle oscillations we observe in our study. And then we construct the complex analytic signal, which is obtained by using a Hilbert transform. We can conveniently, here AK refers to the amplitude and theta k is the phase of the oscillations. We can conveniently normalize the amplitude of the oscillations by taking q dot k divided by a dot k, ak, which is nothing but sine of theta k, where theta is the phase. Therefore, there is a dependence of amplitude on the phase itself. So in this figure, we plot the normalized amplitudes. We plot the normalized amplitudes as well as the phase difference between different burner pairs. From B, we see that the amplitudes line up mostly, but there are like multiple places where the amplitudes between different burner pairs do not line up. This is seen much more clearly when we look at the phase difference between different burners. We can see that from this red regions, regions enclosed in this red boxes, that there are significant phase slips between different burner pairs. So this state is referred to as partial intermittent phase synchronization. On the other hand, if we now focus on the dynamics observed during low amplitude instability, we observe a flame that is only stabilized along the shear layers in the phase averaged images. So B is phase averaged at the pressure maxima, C is at the mean, and D is pressure minima. And from the local flame dynamics, we observe that the flame from the amplitude, we see that these amplitudes line up more and more often as compared to the periodic part of intermittency. And this is seen much more clearly from the phase plot, where we see that there is only very few phase slips in the system. So this state is referred to as weak synchronization. Finally, during high amplitude instability, from the phase averaged image at pressure maxima, we observe that there is a very strong amount of pressure heat release rate oscillations, and the flame sort of propagates into the inner reach circulation zone, as can be seen here. From the local flame dynamics, you can see that the amplitudes almost always lines up, and from the phase dynamics also shows the same, that there is no phase slips in the system. Therefore, this state kind of is referred to as the state of perfect synchronization. Now we want to quantify these synchronization characteristics. In order to do that, we define the phase locking value, which is a temporal synchronization measure, and we introduce the Kuramoto order parameter, which is a spatial synchronization measure. In the temporal measure, we consider the phase difference between any two given signal, and if the PLV value is 0, that means that those two signals are desynchronized. Whereas if the two signals are equal, the PLV for two signal is 1, that means that they are completely synchronized. Similarly, for the Kuramoto order parameter, this is for each individual each individual burner, and the average is taken across all the burners. Therefore, if we have R is equals to 0, we have spatial desynchrony, whereas if we have R equals to 1, we have perfect spatial synchrony amongst the 8 burners. Here NB would be equals to 8. Now here we plot the flame-flame interaction in A and flame acoustic interaction in B using PLV. In both these cases, we see that during combustion noise and intermittency, we have desynchrony and partial synchrony respectively. Whereas during low amplitude instability, we see that burners themselves are very weakly synchronized to each other, and they are synchronized with the acoustic pressure fluctuations also in a very weak manner. Whereas during the state of high amplitude thermoacoustic instability, the burners are themselves completely synchronized, and the burners are synchronized perfectly with the acoustic fluctuations. In C, we plot the Kuramoto order parameter, and we again see that for combustion noise, there is a lot of fluctuations. That is because we cannot define the phase properly because the oscillations are chaotic. But for the intermittent oscillations, we see that sometimes there is a very high value of R. So this corresponds to intermittent synchronization of burners during the periodic oscillations, the periodic epochs of intermittency. During low amplitude instability, we again see that the value R fluctuates between 0.1 to 0.5 to 1, indicating that we have weak synchronization. And finally, during high amplitude instability, we have complete synchronization amongst all the burners. Now to conclude, we report the first experimental evidence of secondary bifurcation in a turbulent annular combustor. We quantify the flame-flame interaction. We develop a very novel synchronization theory in a novel manner to study the flame-flame and flame acoustic interaction taking place inside the burner to obtain more and more insights in the local flame dynamics. Now to summarize these dynamics, we have during combustion noise, we have incoherent and asynchronous flame dynamics, which ensures that there is no fulfillment of the Rayleigh criteria. During intermittency, there is partially intermittently synchronized burners are observed, which again would indicate there is some intermittent fulfillment of the Rayleigh criteria. During low amplitude thermoacoustic instability, we have weak synchronization. which indicates that the Rayleigh criteria is only weakly fulfilled. During high amplitude instability, we have complete synchronization amongst all the burners as well as the burners and the pressure oscillation. Therefore, this leads to a complete fulfillment of the Rayleigh criteria. Therefore, the different level of synchronization among different burners lead to different observed dynamics in the combustor. Thank you. And I'd like to acknowledge all our lab members.